Hi, and welcome to our first lecture on k-means clustering. In this lecture, we will be learning about nuts and bolts behind the k-means clustering algorithm. So let's begin. And first, let's answer this high-level question. Let's answer what is k-means. And the first thing you should know is that k-means is unsupervised learning algorithm, meaning that k-means requires no label data, k-means requires no training. You can simply load this dataset of yours, perform some pre-processing if needed, and you can run k-means with this data. And the next important key point is that k-means is used to find structure in your data by grouping this data into k clusters or k groups. And this number k, which represents number of groups, is user-defined. So you could write k equals 3, and by doing this you would say, hey, k means here is my data, please find 3 groups in this data. And simply by eyeballing this data, you can see that there is a structure, there are these 3 groups, and if you run k-means on this data, in ideal case, you would get this result right here. So k-means would detect this structure in this data and would assign each data point to a certain group. And now let's talk about these groups for a second. So groups are nothing but a collection of similar items, and we need a way to measure this similarity. And in this case, we would use Euclidean distance to do so. And finally, aside from assigning each data point to a certain group, k-means will also generate centroids for each cluster, for each group. And centroid is nothing but an average instance of this group. So now let's go further and let's learn more about Euclidean distance. And let's first say that we have a new dataset. Let's say that this dataset has 2 features, feature 1 and feature 2, and let's say that this dataset only has 2 data points, x and epsilon. So Euclidean distance is this straight line distance between our data points, between 2 data points, in a coordinate system which is defined by our features. And we can calculate Euclidean distance by using this formula right here. So we should go over all of our features, and for each feature we should find a difference in values between our 2 data points. So let's start with feature 1. We should write down 4 minus 1. We should square this. And after that, we go to feature 2. And for feature 2, we get 6 minus 3. And we will square this as well. And in the end, we will calculate the square root of this expression. And this results in 4.24, which is Euclidean distance between points x and epsilon. And it should be pretty intuitive that Euclidean distance is measure of dissimilarity between our points, because the further away our data points are in this feature space, means that they are different. And if they are close in this feature space, it means that they have similar values for all of these characteristics, for all of these features. Hence, the points will be similar if Euclidean distance between our data points is low. And this is everything you should know about Euclidean distance in order to understand k-means clustering. And now let's go further And let's learn about these steps that are involved in k-means clustering. And in this case, we will be learning about this L-Lloyd version, which is the most popular one. So the first step in k-means clustering is user-defined. So we should choose number of clusters. And let's say that we set k to 3, meaning that we want to split our data into 3 groups. The next step is cluster centroid initialization, and this is usually done by selecting several points from our dataset to be our starting centroids. So this choice of centroids is something that's perfectly okay. And after that, we will repeat these two steps, this step and this step, until convergence. And by convergence, we mean until we reach some stationary state, some stable state. So through this repetitive routine, through these iterations, we should go from these centroids to these centroids. And our iterative part includes these two steps. In the first step, we assign points to the closest cluster centroid. And in the second step, we compute new cluster centroids by averaging all points within each cluster. And this might sound a bit unclear at the moment, but don't worry about it. Now we will go through all the steps in a great detail. So let's start with initialization. And in its simplest form, initialization is completely random. So what we will do in order to initialize cluster centroids is pick several data points, and if our k equals to 3, we would simply have to select 3 data points, and we could do something like this. And now let's go on and see example of such an initialization. So here is our data set, and after initialization, we have picked 3 points, and we have assigned identity to each of those points. So the green one is 0, it represents cluster 0, the yellow one represents cluster 1, while the blue one represents cluster 2. And after this, we start our iterations, and the first step is cluster assignment. So here are our centroids right here, and the first thing we will do is assign each point to the nearest centroid, and we will use Euclidean distance to measure this distance. So all of these data points will become blue, all of these data points will become yellow, and all of these data points right here will become green. Which leads us to our next step. This leads us to centroid update. So simply by looking at this plot right here, you can see that something is not right. So we said that this centroid should be the good representative of our cluster, but look at this yellow centroid right here. You can see that the majority of data points are here, but centroid is outside, somewhere outside. And in this step, we should fix that. So we will move our centroids to a new location in order to make them a good representative of this current cluster. And we will do this by calculating new coordinates for each centroid. And let's take the example of this yellow cluster. We will do this by by calculating average value of feature 1 for all the yellow data points, and average value of feature 2 for all the data points, and we would use this as our new centroid. And we will do the same thing for this green cluster and for this blue cluster. And here is the result. You can see that the yellow centroid is inside of this area right here. And after that, we will repeat this again and again. So let's go to this first plot. And you can see that even though we have moved this centroid here, something is still not right. You can see that these blue points are now closer to this centroid than they are to this centroid. And this calls for a new cluster assignment where each data point will be assigned to the closest cluster centroid. After that, we will update centroids and so on until this happens. You can see that even though we are doing updates, we are doing assignments, nothing really changes here. The centroids will no longer move. And when you see a state like this, where nothing new happens, you can say that your algorithm has converged. And in this moment, you should stop the iterations and declare that algorithm has finished. And this wraps up our today's lecture. So in this lecture, we have learned about k-means, we have learned about nuts and bolts, we have learned about this first part about the initialization, we have learned about algorithm steps, these steps that go on again and again until the algorithm converges, and we have also learned what k-means convergence really means. And this is it. See you in the next lecture where we will be learning about suboptimal solutions for k-means and how to avoid them.